John Scott Haldane is undoubtedly the most renowned researcher in the entire history of decompression. At the beginning of the 20th century, the procedure followed by the divers was identical to that used by the tubists. To avoid decompression sickness, the ascent to the surface was as slow as possible, in order to reduce the pressure evenly and continuously. Thus, for a diver working at a depth of 30 meters, the return to normal pressure took 1 hour, regardless of the time spent at that depth. Haldane proposed to the British Royal Navy to conduct an experimental campaign to develop a more suitable method for deep diving. The Royal Navy set him the goal of allowing human intervention at a depth of 60 fathoms, that is just over 55 meters. The challenge was significant. Haldane knew that decompression sickness were caused by nitrogen. He focused only on the effects of this gas. His own research allowed him to consider that nitrogen in the inhaled air passes instantly into the blood. Thus, the arterial blood is, from the start of exposure to compressed air, saturated with a partial pressure of nitrogen in the lungs. As it circulates in the arteries, this blood carries nitrogen into the tissues. The excess nitrogen in the arterial blood diffuses into the tissues. The venous blood returns to the lungs, where it is recharged with nitrogen and then circulates back into the arterial system to deliver a new load of gas to the tissues. Through the repetition of this process, the tissues gradually become increasingly saturated. The diffusion equation established by Adolf Fick in 1855 could describe the gas exchange between blood and tissues, provided that the parameters of the different tissues in the human body were determined. The saturation of a tissue, whatever it may be, depends on the amount of blood supply and the solubility of nitrogen in that tissue. These two parameters vary considerably in the different parts of the body, and Haldane deduced that the saturation rate varies accordingly from one tissue to another. He assumes that bones do not absorb nitrogen, and that semi-liquid tissues saturate in the same proportion as blood. He made an exception for fat, based on a study showing that fatty tissues absorb, per unit weight, 6 times more nitrogen than blood. By estimating the weights of blood and fat in a normally nourished man, Haldane calculated the amount of nitrogen absorbed by fat after one full cycle of blood circulation, following sudden exposure to a given pressure. He added the amount of nitrogen absorbed by the same tissue during a second cycle, then a third, and so on. Haldane determined that half of the nitrogen in the blood passes into the tissues after 23 cycles of circulation. Every 23 cycles, the tissues gain half of the difference between the partial pressure of nitrogen in the blood and the amount they already contain. Haldane had just uncovered the saturation curve of the human body's tissues. Determining the law to obtain this curve was now a piece of cake. He defined the rate of saturation of a tissue by its period, which is simply the time required for the nitrogen pressure in that tissue to reach half of the pressure in the blood. Haldane estimated that a resting person's blood completes one full cycle in 1 minute. The 23 circulation cycle required to reach half of the nitrogen pressure gradient correspond to a period of 23 minutes. If these assumptions are valid for a person exposed to compressed air, complete saturation would only be reached after more than 2 hours under pressure. Haldane was well aware that some parts of the body must saturate much more quickly than this calculation suggests. He referred to a study in which urine samples were taken from subjects exposed to high pressure. The authors reported that the samples were saturated to the partial pressure of nitrogen after about 10 minutes, and conversely, upon returning to normal pressure, the excess nitrogen disappeared within a few minutes. This corresponds to a saturation rate 10 times faster than that calculated by Haldane. From this, Haldane deduced that some tissues saturate faster while others saturate more slowly. He conducted experiments on animals and observed that the smaller the animals, the faster the tissue saturated. He then decided to continue his research with goats because they were easy to obtain and were the largest animals he could place in the experimental hyperbaric chamber he had. His experiments showed that it took at least 3 hours for a goat's slowest tissues to be fully saturated. Haldane estimated that, based on their respective weights, it would take around 5 hours for a normally built man to reach the same saturation. In humans, the slowest tissues would therefore have a period of 50 minutes. Haldane chose to take into account a compartment with 75-minute period. He stated that there was no need to account for slower saturation rate unless the percentage of fat was unusually high. He developed the model that would bear his name, with 5 theoretical compartments of periods 5, 10, 20, 40, and 75 minutes, meant to represent the diversity of tissues in the human body. He was now able to calculate the nitrogen pressure accumulated in each of these compartments. All that remained was to define the rules for safe decompression. He proposed the principle of symmetrical desaturation with respect to saturation, provided physiological conditions remain constant. The model used for saturation also worked for the elimination of excess nitrogen in the tissues. To determine the partial pressure of nitrogen the human body could tolerate without risking decompression sickness, Haldane once again relied on the experience of the tubists. On construction sites and in mine shafts, no special precautions were necessary as long as the inhaled air pressure did not exceed double the atmospheric pressure. He hypothesized that if there was no danger in moving from 2 atmospheres to 1, then there would be no danger in moving from 4 to 2 or from 6 to 3. Based on this principle, he developed a revolutionary decompression process that involved rapidly reducing the pressure by half and then organizing the ascent so that no part of the body would ever contain more than double the ambient pressure. To verify the validity of this procedure, Haldane conducted numerous experiments on animals and then on Lieutenant Dament and Gunner Cato, both in experimental chambers and in actual dives. In 1908, Haldane published the very first decompression tables.